Welcome back. Today we're going to be looking at the graphs of exponential functions. In section 6.1 we explored exponential functions and how to define them, how to find certain characteristics about them, and how to plug and chug numbers into them. Today we're going to be looking at the graphs and how each variable in the exponential function affects the graph. So if you remember, our main function or our toolkit function for exponentials last week was f of x equals abx. Today we're going to be looking at, if we remove that a for just a little bit and we look at the parent function, or the original function b of x, what each thing does. So what we're going to do to start is we're going to sketch the graph. We're going to sketch the graph 4 raised to the x power. In order to do this, I'm going to start by graphing a few key points, and we'll label those points as we plot them. So we have x comma f of x, and if we start with the 0 in the middle, and we say 4 raised to the 0th power is 1, we'll get 0, 1 as our y-intercept. And then if we just take it to the next step, the next easiest one, if you plug in a 1 and you go 4 raised to the 1 is 4, we'll get our second point, and these are the most important 2 points to graph when you're sketching an exponential function. Everything else is going to grow pretty fast and usually jump off the graph. If you go to 2, I think we'll end up at 16 because 4 squared is 16. That's off the graph. So because that exponential growth is so quick, it's going to go off the graph really quick, and you can just sketch those points. And then likewise, we're going to go backwards, knowing that it will never get to the negative side of things because there's no value that you could plug into x that would get you a negative number. So like for instance, if we plug in -1, we'll end up with 1/4. And if we plug in -2, we'll end up with 1/16. And that y value, or that f of x value, will keep getting smaller and smaller, but it will never hit 0 and it will never approach 0. The reason being, if you think about it, take 4 to the x and set it equal to 0 and try to solve for that. You can try any number for x in the world. Try negative 100, try 100, try 1/2, which would be the square root. There's no number you can plug into that x to get you 0. We'll explore that more next week with logarithms, but for today we're just looking at these graphs and seeing if we can graph them by plotting a few points and analyzing some key features. The next thing we're going to do is we're going to look at the domain, because this arrow goes forever to the left and this arrow goes forever to the right. Even though it looks like it's going up, it's not an asymptote. So our domain is going to be all real numbers, or -infinity to infinity. Then we're going to look at the range. Say, okay, well, what's the smallest possible y value of this number? Well, we know it can never get to 0, but if we keep going forever, we'll get infinitely close to 0, not including it, and then we'll go up forever on the right. And the last thing we need to know is, what is the horizontal asymptote? There's not a vertical asymptote on this function because there's no number divided by 0, but it does have a horizontal asymptote. The exponential function has a horizontal asymptote for the parent function, and for many of them that don't have vertical shifts at the x-axis or the line y equals 0. Notice not a lot changed there besides the points we plotted from the original parent function, where your value of your base is going to be your value of your first point. So you notice we plotted the same 2 points that they plotted on this graph, where b just changed, and it was applied using the value of our base, in this case 4. If we wanted to plot a couple more points just to be safe, we could say -1 gets to 1/4. So -1 should have been 1/4, which maybe we could sketch a little prettier. And -2 is 1/16, so it gets even closer to the line. And so if we wanted to sketch that right side a little bit prettier, just to make sure we're accurate, we could go like that. It's going to get really hard to draw once you get into this 1/16, if we get to 1/32, all those things. Okay, let's keep going. We're going to look at a shift next. We only got 2 more problems. We're just going to look at what shifts do to this function. So we're going to graph this function saying, okay, our original 2 points, the 2 points we were going to plot, if we were going to do a no shift graph, right? If we were going to do the normal x, let's call it g of x, where g of x is 2 to the x. Sometimes it's cool to look at the original graph before you do your shift. If you plug in 0 to 2 of x, you'd get anything to the 0th as 1. And if you plugged in 1, you would have got 2. So if we were to graph that, it would look like the point 0, 1, and the point 1, 2, and then we would build our exponential out of there. But we know that this graph actually has a couple shifts on it. We have a shift on the outside, which if you remember from our shift function, shifts it up 3, and we have a shift on the inside of the exponent, which looks like it's going to take it to the left, but in fact it takes it to the right by 1. because remember, anything inside the function might be opposite of what you'd expect. If it's negative, it goes to the right. If it's positive, it goes to the left. All right, so let's get this thing and we'll graph it. The first thing I'm going to do is I'm going to shift the horizontal asymptote. In our parent function, the horizontal asymptote was at the line y equals 0. But because this is shifted up 3, I'm going to take that line and move it up to the line y equals 3. So there's a vertical shift of 3 of my function. And then there was a horizontal shift of 1 of my function. Now it's not an asymptote, so we can't draw it. But we just have to know where our points were starting and where they're going to end up. So our first point was going to be at 0, 1, right? But we shifted it up 3. So we would say it would be, so if we started at 0, 1, and then I'll erase these, shifted up 3, 1, 2, 3, and shifted to the right 1, we've got a point at 1, 4. And if you plug and chug some numbers into our function, you'll see that if you plug 1 in, you'll get 4. Let's check that real quick. F of 1 equals 2 to the 1 minus 1 plus 3. Anything to the 0th power is 1 plus 3 equals 4. It worked out. Our second point we were going to plot was 1, 2. But if we take the point 1, 2, and we shift it up 3, 1, 2, 3, and over 1, we get the point 2, 5. Whoops. 1, 4, 2, 5. And so using those 2 points, we can graph what our exponential is going to look like. And we can look at the domain again. Nothing in the domain has changed. We're still going from negative infinity to infinity. We can look at the range, where the range is starting at. Now instead of starting at 0, it's going to start with that vertical shift. So it's going to start at 3, and it's going to go up to infinity. And our asymptote, we've already talked about, has changed. It's a horizontal asymptote, and it's changed from the line, which is the x-axis, up 3. So our new horizontal asymptote is y equals 3. All right, so those are how to analyze a graph and look at some key features. We're going to reflect it one time, and then we'll call it a day for graphing exponential functions. All right, so reflections of the parent function. Find and graph an equation for g of x, which reflects f of x about the y-axis. All right, so what we're going to do first is graph f of x, comma f of x. Let's plug in those 2 key points again. I'm going to plug in 0, and if I plug in 0, anything to the 0th power is 1, so we'll get 1. And if I plug in 1, you'll get the identity under exponentiation, so you get 1, 1.25, and we'll plot those 2 points as our original function. 0, 1, 1, 1.25. So we've got a slightly slower growing exponential function. Now it's asking us to reflect this about the y-axis. So if we still have our horizontal asymptote at 0 because nothing's changed with the vertical shift. And all we're going to do is take each point and reflect it across the y-axis. So this point will go there. The line on y-axis will stay the same. And we'll see that we end up with something that looks like an exponential decay. And so, something interesting to point out is that when we reflect across the y-axis, we get exponential decay. And if you remember from back in the day, what y-axis reflections look like, they were a negative sign on the inside of the function, because that's a horizontal reflection. And so if you take f of x equals 1.25 raised to the x, you say, what did y-axis reflection mean? It meant horizontal reflection, which meant adding a negative on the inside. And so that would make that g of x, you would leave the outside the same, and you would add a negative sign inside of the function, or right next to the variable. And that makes sense because now we've got exponential decay happening. And we've got our graph. Does it ask for anything else? It does. It asks for the domain. Let's go ahead and get that. The domain didn't change. It still goes left forever and right forever. Negative infinity to infinity. The range did not change because we didn't shift up or down. So we're still going from 0 to infinity. And the asymptote did not change. We still have y equals 0 as our horizontal asymptote. And that green function is our g of x, or our vertically reflected, or our y-axis reflection of f of x. All right, thank you for watching. Keep watching to move on to logarithmic functions and graph of logarithmic functions in section 6.3 and 6.4. And I will see you next time.